Welcome all. Now we are going to discuss the concept of non-measurable sets. Okay, first we have a lemma number 16. The statement is, let E be a bounded measurable set of real numbers. Suppose there is a bounded countably infinite set of real numbers lambda, for which the collection of translates of E, that is set of all lambda plus E or lambda element of lambda, is disjoint, then measure of E equal to 0. Okay, so let's discuss the proof. We have given E be a bounded measurable subset of R and lambda be a bounded countably infinite subset of R, for which the collection of all translates lambda plus E is disjoint. Okay, now we are going to check the measure of union lambda element of lambda, lambda plus E. That is, by countable additivity of Lebesgue measure, we can write it as summation lambda over lambda measure of lambda plus E. We know outer measure is translation invariant, and so measure is also translation invariant. So we can write measure of lambda plus E is equal to measure of E, and we get equation number 1. Okay. Also we have E and lambda are bounded sets. Therefore, all translates lambda plus E of E are bounded for every lambda element of lambda. So the union is also bounded, and so the measure will be finite. That is, measure of union lambda plus E is less than infinity. From equation 1 we know that that is equal to summation measure of E, that should be less than infinity. Okay, this means that measure of E should be equal to 0. Because if measure of E greater than 0, and since lambda is countably infinite, that will lead to the result that summation measure of E equal to infinity. Okay, but we have to say that summation measure of E is less than infinity. So this also happens only if measure of E equal to 0. So that's the lemma. Next we have the important theorem, theorem number 17, called Vitali. The statement is, any set E of real numbers with positive outer measure contains a subset that fails to be measurable. Okay, so every set E of real numbers with positive outer measure has a subset that fails to be measurable. Suppose we are discussing the proof first in the case of bounded sets and then the case of unbounded sets. Okay, suppose E is bounded, then we know that m star of E is less than infinity, and given E is a set of real numbers with positive outer measure, so m star of E is greater than 0 also. Okay, now we are going to define a relation on the set E called rational equivalence, as for any two elements x and y element of capital E, x related to y if and only if x minus y is rational, that is, their difference is rational. So this relation is an equivalence relation on E. Okay, to prove that it's an equivalence relation, we have to prove reflexivity, symmetricity and transitivity. Okay, that is, for every x element of E, if we check x minus x, that is 0, it's clearly a rational number. So x related to x for every x element of E means the relation tilde is reflexive. And if we suppose x related to y, then x minus y is rational. Clearly y minus x is also rational, that means y related to x, so the relation is symmetric. And if we suppose x related to y and y related to z, then we can clearly obtain x related to z, that is, the relation is transitive also. This means that the relation is an equivalence relation on E. Then we can partition capital E into disjoint classes, that is, we can partition capital E into equivalent classes under this relation. Now we are picking each member, picking one member from each equivalent class and forming a subset CE of capital E. Okay, that is, CE be the subset of E that contains exactly one member from each equivalent class under this relation. Okay, then we can characterize CE as follows. For x comma y element of CE, their difference x minus y is clearly not rational, because if their relation is if their difference is rational, then they are belongs to the same equivalent class. So we are taking only one member from each equivalent class. So x minus y is clearly not rational if they both belongs to CE. Okay. Also, for any x element of the set E, there is a point in CE C such that x minus C is rational. Okay. And also, for any lambda subset of Q, the set of all translates of CE, that is set of all lambda plus CE, where lambda element of lambda is clearly disjoint by this all conditions. Now we are going to claim that this set CE that we found above is not measurable. Okay, we have CE is a subset of E. Now we are claiming that this CE is not measurable. Okay. We have given capital E is a subset of R. Now we are considering the case that E is bounded, and so we can find a subset, we can find a closed interval minus BB such that E is fully contained in closed interval minus BB for some B element of R. Since this will be happen because E is bounded. Okay. Now suppose if possible that the set CE is measurable. Now we will suppose CE measurable and will arrive at a contradiction. Okay. We are choosing lambda to be closed interval minus 2b to be intersection with the rational numbers, so that lambda is countably infinite and bounded subset of Q. Okay. Then we know that the set of all translates of CE, that is set of all lambda plus CE, where lambda element of lambda is disjoint. So this will lead to the result that measure of CE equal to 0 by the lemma above. Okay, because we are assuming that CE is measurable and we found a countably infinite bounded subset lambda such that all translates lambda plus CE is disjoint, then by the above lemma we can say that measure of CE is equal to 0. Let it be equation number 2. Now we are checking the measure of union lambda over lambda, lambda plus CE, that is by countable additivity, that is equal to summation lambda element of lambda measure of lambda plus CE, but measure of lambda plus CE is equal to measure of CE. So we get summation lambda over lambda measure of CE, that is equal to 0 because measure of CE equal to 0 in equation 2. That is we obtained measure of union over lambda, lambda plus CE is equal to 0. Let it be equation number 3. Now choose x element of capital set, choose x element of capital E, and we know there is an element C in CE such that x minus C is rational. Let it be Q, that is x minus C equal to Q, where Q is any rational number. But we know that x and C belongs to capital E, and capital E is a subset of closed interval minus BB. This means that the distance between these 2 points x and C will be a maximum of 2b. Okay, that is modulus of x minus C is less than or equal to 2b. That means x minus C is an element of closed interval minus 2b, 2b. What is x minus C? That is Q. Means Q is an element of this closed interval minus 2b, 2b. Okay, but Q is rational also. So Q is an element of closed interval minus 2b, 2b intersection with the Q. This is actually we have chosen as lambda. So this means that Q is an element of lambda. So there is a translate Q plus CE in the above collection. Thus we have x minus c is equal to q means x is equal to q plus c, and q plus c is an element of q plus ce, that translate q plus ce, and that is a subset of union of all translates, okay, because q is an element of lambda. So q plus ce is a subset of union lambda plus ce, where lambda element of lambda. This means that we have chosen an element x element of E, and we have found that x is an element of the union of all translates. This means that E is a subset of union of all translates of CE. Okay, so we are checking the measure. We obtain that measure of E is less than or equal to measure of the union of all translates, and using equation 3 we can say that this is equal to 0. Means measure of E is less than or equal to 0, but this means that measure of E equal to 0 because measure is non-negative and measure of E equal to 0. But we have chosen a set E to be a set of real numbers with outer measure positive, right? So this is not possible, and this is a contradiction. So we have arrived at a contradiction. Therefore, as we claimed, we arrived at the conclusion that CE is not measurable. Okay, now let's consider the case of unbounded sets. That is, let E be unbounded. Then we know that E can be expressed as a union of bounded disjoint measurable sets EK, and we have proved the result for bounded sets, and each EK is bounded, and so each EK contains a non-measurable subset, and so capital E also contains a non-measurable subset. So this is very important theorem, that every subset of real numbers with positive outer measure contains a subset which is non-measurable. Okay, and we have one more small theorem here, theorem number 18. The statement is there are disjoint sets of real numbers a and b for which m star of a union b is less than m star of a plus m star of b. Okay, let's discuss the proof. If possible, we may assume that m star of a union b is equal to m star of a plus m star of b for every disjoint pairs of sets a and b. Okay, this means that every set of real numbers is measurable. Since we can express every set as a disjoint union of singleton sets, we can say by this that every set is measurable. But this is a contradiction for the above theorem, that there are non-measurable subsets. So we can say that m star of a union b equal to m star of a plus m star of b for every disjoint pairs of sets a and b is not true. That means there are subsets, disjoint subsets a and b, such that m star of a union b is less than m star of a plus m star of b. That is, m star of a union b is less than m star of a plus m star of b for some disjoint pairs of sets a and b. Okay, thank you.